Alternating current systems began commercially in the United States in 1886. The outstanding advantage of the AC system is the relative ease with which alternating voltages can be generated and transformed in magnitude. At present, most of the electrical energy consumed in the United States is generated, transmitted, and utilized in the form of alternating current. In the normal AC power distribution system, the AC voltage is developed by large AC generators or dynamos, which are driven by water power, steam, or nuclear power. The output voltage from these generators is quite high, about 13,800 volts or greater. If the electrical energy were transmitted at this voltage, the line loss from the power lines would be very high due to the larger amount of power being delivered. For this reason, this high AC voltage is fed into large transformers to be boosted to an even greater value. These large transformers will boost the 13,800 volts upwards to 150,000 volts or even greater. This high AC voltage is then transmitted over the high-tension transmission lines for distances ranging up to several hundreds of miles. At 150,000 volts, the current will be low for a given amount of power, so the line losses will be low. Of course, this extremely high voltage cannot be used safely in homes, so it must be lowered to some safer value, usually 120 volts, before it is brought into the homes of the consumers. This task is also performed by transformers. As you will see, transformers can be used to change low-value AC voltages into high-value AC voltages and vice versa, and it is done very efficiently. For this reason, the transformer costs very little to operate. Transformers, however, cannot be used with DC voltages, and no other means of transforming low values of DC into high-value DC voltages in an efficient manner have been developed. For this reason, alternating current is used almost exclusively, as was mentioned earlier. In Part 4 of the You Can Do video series, you will learn that we must change the AC voltage from the power lines into a DC voltage for operation of electronic circuits. This is performed by circuits known as rectifier circuits, which are the heart of the power supply system. You will also learn that when we apply this DC voltage to certain types of transistors or integrated circuits or other types of semiconductor devices, these circuits will generate an AC voltage. This type of circuit is called an oscillator. You will learn more about oscillators in Part 6 of this series. What is AC? By definition, AC stands for alternating current. AC is a current that periodically changes in magnitude and direction. Here we see a diagram of a circuit that can be used to produce an alternating current. When the switch is in position 1, the electrons will flow from the negative side of the battery through the switch and into the resistor at point A. Next, the current will flow through the resistor to point B and then return to the positive side of the battery. When the switch is thrown from position 1 to position 2, the current will flow from the negative side of the battery into the resistor at point B, through the resistor to point A, then through the switch and back to the positive side of the battery. If we continue throwing the switch from position 1 to position 2 and then from 2 to 1 at 1 second intervals, there will be an alternating voltage across the load resistor. The current flows through the load resistor and will be reversing itself at 1 second intervals. The AC circuit we have just described is a very simple one, and the AC voltage, which is generated commercially, is considerably different. The most common type of AC wave and the type most practical to generate is called a sine wave. Here we see a graph of a sine wave. The voltage is plotted on a vertical axis and the time in seconds is plotted on a horizontal axis. As you see, the voltage is changing in both magnitude and direction, so it fits the definition of alternating current. Let's examine this graph of the AC voltage. At 0 time, the voltage is 0. At 1/240th of a second later, the voltage has increased to its maximum peak potential. The voltage gradually decreases until at 1/120th of a second, the voltage has again reached 0. Now the voltage begins to build in a negative direction. At 1/180th of a second, the voltage has reached its maximum negative peak potential. In the time span from 1/80th to 1/60th of a second, the voltage decreases to 0 volts again. This is one cycle of the AC voltage. By definition, a cycle is one complete succession of events. We notice that the voltage started at one value, went through all the variations, then returned to its original value to complete one cycle. Notice that each cycle occurred in 1/60th of a second. This AC voltage is also called a 60-cycle AC voltage. Another term which is used in connection with AC is alternation. An alternation is 1/2 of an AC cycle. On the graph of the sine wave, that portion of the sine wave from 0 to 1/120th of a second is one alternation, and the portion of the sine wave from 1/120th of a second to 1/60th of a second is the second alternation which occurs in the sine wave cycle. Another term which is used in conjunction with AC voltages is frequency. Frequency is the number of times anything happens in a given time period. When applied to AC voltage, the frequency represents the number of cycles which occurs in 1 second. The frequency of the wave shown here would be 60 cycles per second, or 60 hertz. The AC voltages supplied to most homes in the United States have a frequency of 60 cycles per second. The frequency of an AC voltage is very important. Frequencies above 150,000 cycles per second are called radio frequencies. Radio frequency signals will range from thousands to millions of cycles per second. The terms K, M, and G are used to designate thousands of cycles per second, millions of cycles per second, and thousands of millions of cycles per second. You will see these three terms used a lot when dealing with radio frequency signals. In 1966, a new term was adopted to represent cycles per second. The term is Hertz. It was used to honor one of the early experimenters in radio, Heinrich Hertz. Thus the term which we used before for 60 cycles per second, which was 60 Hertz. The written abbreviation for Hertz is Hz. The period of the wave is defined as the time required for one cycle to occur. If the frequency of a wave is 60 Hertz, then each individual cycle would last for a period of 1/60th of a second. The period of a frequency is measured in time. To calculate for the period of a signal, you divide the frequency of the signal into 1, or T equals 1 over F. In this formula, T represents the period in seconds, F represents the frequency in cycles per second, or Hertz. In your studies of direct current, you learn that voltage caused the current to flow through the circuit. This also holds true for alternating current circuits. Electrons flowing through a resistor generate heat regardless of whether they flow steadily in one direction or reverse their direction periodically. When AC current flows through the filament in a light bulb, the filament will illuminate. If the frequency of the AC is above 30 Hertz, the bulb will appear to be giving off a steady light. Actually, the filament cools off somewhat as the alternating current goes through zero, but the eye does not detect this. Here we see a graph of an AC voltage being applied across a resistor. We have plotted both the voltage and the current. Notice the points where the voltage passes through zero are the same points where the current passes through zero. Also notice that the voltage and current reach their peak values at the same time. This is true for a circuit containing resistance, but it is not true if the circuit contains a coil or a capacitor or both. We shall learn more about coils and capacitors later. When the two curves coincide as they do in our graph, they are said to be in phase. When they do not coincide, they are said to be out of phase. Here we see another graph of a sine wave, but this time the time axis is marked off in degrees instead of seconds. This is possible because a cycle represents one complete succession of events. Therefore, the cycle of an AC wave may be broken into degrees. There are 360 degrees to one cycle. A cycle may be further broken down into quadrants of 90 degrees each. Notice at 0 degrees and 180 degrees, the voltage of the sine wave is 0, and at 90 degrees and 270 degrees, the voltage of the sine wave is at its peak value. The peak value of the sine wave is the greatest value to which the voltage or current will rise. If lines are placed on the graph that intersect the sine wave curve, Each of these lines will have a different length and will represent the voltage at some particular point in time. The voltage at this instant in time is known as the instantaneous voltage of the waveform. From this graph, it is evident that the instantaneous voltage from a sine wave depends on the particular instant at which the voltage is measured. By referring to this table, you can find the value of a sine wave at any instant of time. For example, if the peak value of a sine wave is 100 volts, what is the value of the voltage at 20 degrees? By looking at this table, we see the sine of 20 degrees is 0.34. Therefore, if we multiply 0.34 times 100, we see that the instantaneous voltage at 20 degrees is 34 volts. At 140 degrees, the sine is 0.643, so the instantaneous voltage at 140 degrees is 64.3 volts. And at 240 degrees, the sine is minus 0.866, so the instantaneous voltage at 240 degrees is minus 86.6 volts.